Okay, so this is work in collaboration with Alan Gable, who's a former PhD student of mine, Marina Kogan, who's a former PhD student of Aaron Clausette, who is a close friend of mine and collaborator at University of Colorado. Now, what I want to present to you today is like very simple, and in fact, I want to tell you just sort of philosophically, like some aspect of my research is driven by everyday things. This is just looking at basketball, and so in the field of statistical physics, I think what makes it so beautiful is that there's so much out there that you can look at and get data and start making theories and having beautiful observations. And India being a crowded, somewhat chaotic country, there's all kinds of things you can observe. Traffic patterns, cows crossing the street, how many people are in these little auto rickshaws, what's the distribution number of people in them. There's just all kinds of things where, it's all around you. You just have to open your eyes. And so that's basically what I'm going to present to you today, is just a sort of cynical look at basketball scoring statistics. So the question is the following. Can basketball be described by a random walk? Now, for those of you, first of all, let me ask a question. How many people like basketball? How many people couldn't care less about basketball? Okay. How many people don't know anything about basketball? Do they? Okay. So for those of you who know nothing about basketball, let me tell you the rules. The basic rules. It's to win a game, and there are 2 baskets at either end of a basketball court, and alternate teams are trying to get the ball into the basket. And every time you score a basket, the other team gets the ball, and they try and score a basket in the other direction. And that's basically all there is to it. And because there's this back and forth flow that when one team scores, the other team gets the basketball and the other team scores, there is kind of a stochastic flow to the scoring statistics. And I want to ask, is basketball described by a pure random walk? So this is maybe I should turn up the sound a little bit. Turn up some sound. Just to give you a sense like what basketball. So this is the entertainment portion of the talk. This guy here is a guy whose name is Julius Erving. He has the name Dr. J because he's a Ph.D. in dunkology. And what he's doing now, this maneuver is called a dunk, where he rises, that's 10 feet above the ground, he's way above it, and he slams the ball from above. This guy was truly amazing. And this guy here, Michael Cooper, was known as the premier defensive specialist in the NBA. He would stop people from scoring baskets. And you see that he gets partway through trying to defend the basket. And he says, holy smokes, I'm screwed. Get me out of here. And he ducks and leaves. So anyways, so that is one view of basketball. Incredibly talented athletes doing amazing feats of athleticism that I could never dream about, ever. But this is my view of what happens in basketball. And I apologize for the cinematography because I'm not much of that, but this is me, and I'm flipping a coin. And so this is my view of what basketball is, just a coin flipping over and over again. So when you see basketball in real NBA basketball games, you see feats of athleticism. What I see, because pardon me? That's right, there is a lot of skill. Yeah, there's not much skill involved in this, but what I'm going to tell you is that the statistics of this is the same as basketball. So now let's turn to some science observations. And again, this is nothing very fancy. The NBA website has all of its data on its website, so you can just take it. And so we took all of 9 seasons of NBA basketball scoring data. And so each basketball game lasts 48 minutes, and you have a trace of what happens in every single basketball game. The game starts out at t equals 0 at 0-0, and then maybe after a few seconds, one team scores and the score is 2-0. Then maybe another team scores as 2-2, and then the first team scores again 4-2, 6-2. And these events happen at certain times in the game, and we have the entire trace. So from this trace, we can then do this kind of representation. We can plot as a function of time going this way, the score difference that way. It starts out 0-0, And so here is a typical basketball game from this 9 seasons of data that we have. It's Chicago versus Denver. And so at the beginning of the game, Denver races to a huge lead, then there's some fluctuations. And then a little bit in the second half, Denver really has a huge lead of almost 20 points. Then Chicago comes back, and at the end of the game, there's a lead change, another lead change. And finally, at the very last second of the game, Denver wins by 1 point. And the question here is, like, is this time trace a random walk? So that is the question that I want to address in this talk. So now let's start looking, as scientists, we have this data set. We just do the absolute things. And so the first thing that you can look at is the scoring rate. And so what I'm plotting here is scoring rate. So that means that for each second of the game, I compute how many score events happened at that point in the game. And this is then the result of 9 seasons of basketball. And roughly speaking, there's huge fluctuations because we're looking at second by second scoring rate. But roughly speaking, there's an average value which is roughly around 0.033, which means that roughly once every 30 seconds or so, there is a scoring event. And so this gives a sense of what the scoring rate is. And so if any of you have ever watched basketball, at least at the professional level, you'll notice that in a time scale of the order of 30 seconds, the ball is advanced to the other end of the court. People are trying to score a basketball. And so there's this characteristic time scale or characteristic rate. So point number 1 is that there's a roughly constant scoring rate. For those of you who have a good eye, you'll see, well, something weird is happening at the end of the first quarter, the first half, the third quarter, the last part of the game. I'll come back to that. The next thing that you can look at is the statistics of times between scoring events. And so what I'm plotting here is, actually, let me show both of them. So I'm plotting now on a logarithmic, semi-logarithmic scale, the probability that there's an interval of length t between scoring events. And so the left plot is where I don't pay attention to which team is actually scoring. So I just keep track of every single scoring event, look at the time between scoring events, and plot it on a semi-logarithmic scale. And you see that there is, at very short times, if someone scores a basket, there's some minimum time that you can advance the ball all the way to the other end of the floor to score another basket. So there's a very small probability of having a scoring interval which is 1 second. That just almost never happens. The typical scoring event is, or the typical interval is of the order of 30 seconds. And in professional basketball, that is dictated by something called a 24-second clock. Namely, when a team scores, the other team has 24 seconds to advance the ball to the other end and throw up a shot that hits the backboard. Otherwise, they lose possession of the ball. So this sets a natural scale for the problem. And you see that beyond 24 seconds, it pretty much fits exponential distribution. If you, instead of looking at the scoring of any team, you say, let me just focus attention on one team and ask, what is the scoring events, the time between scoring events of a single team? Roughly speaking, it's also the same exponential, but with a time scale which is twice as long. One thing which is kind of amusing here is that it turns out that in 9 seasons of NBA basketball, the longest interval where there was not a score was actually more than 6 minutes, more than a single quarter of the game. So even though scoring can sometimes happen very rapidly in the space of a few seconds, every once in a while a team goes cold and you can go 6 minutes without scoring a basket. So this is the first point here is that we argue that the time distribution of times between scoring events is described by a Poisson process. So that's one kind of interesting piece of empirical information. There's another important feature about basketball which has actually been a source of a lot of controversy, and that's the notion of the hot hand. And so, probably you all might feel this intuitively inside of you, that sometimes you're hot and things happen very easily, sometimes you're not hot and you make lots of mistakes, or you trip multiple times on the sidewalk. In basketball, the notion of being hot means that I'm really hot, I just scored a basket, I've really got a good feel, give me the ball again because I'm going to score again. And it turns out that this feeling is actually mostly an illusion. There is no such thing let me qualify it, there's almost no such thing at the level of 10 to the minus 6, no hot hand in basketball. And there's a very famous paper by these social psychologists who did a rudimentary analysis with the technology available at the time, and they found there was no hot hand. And so we did the same analysis, and so what we looked at was the correlation function between scoring events. So imagine, like, suppose that there is a scoring event here, there's a score here, and then a certain time later there's a score here. And so we ask, what is the correlation function between a time delay in one scoring event and a time delay in a later scoring event? So if a team is hot, then score should come very quickly. And if a team is cold, score should be very far separated. And then if you look at the correlation function, this correlation function, you might naturally think gradually should decay, because eventually when you look at scoring events very far separated, they will be uncorrelated. But if there's any correlation, then as you get nearby events, the correlation function should increase. And what we find by the data is that the correlation function, we've normalized it in such a way that it's equal to 1 for self-correlation. But then once we go beyond nearest neighbor correlation, there's basically nothing. So it's showing that scoring in basketball happens at a constant rate with a Poisson distribution of scoring intervals and no correlation between successive scoring intervals. So this is kind of rudimentary facts that seem to suggest that a random walk picture could be appropriate to describe basketball scoring. Here's another thing which is maybe a little bit more familiar to us for those of us who work in random walks, is that we could look at sigma squared, which is I look at the score difference squared average value. And so if this is a random walk process, the score difference should grow linearly with time. Again, this is averaged over 9 seasons of basketball, thousands of games. And you see that for most of the game, the linear fit is not so bad. So that's another piece of evidence that basketball scoring is described as a random walk process. Again, if you're cynical, you say, well, what about here? And I'll come back to that later on. So far, I've just presented you kind of very rudimentary data that seems to suggest that thinking about basketball scoring as a pure random walk is not a bad description. It turns out that a more refined way of looking at basketball scoring statistics is looking at when lead changes occur. One reason for looking at lead changes is that that's when the basketball game is most exciting. If a game is a blowout, then you might stop watching it because there's nothing interesting. One team is obviously going to kill the other team. But lead changes are the most interesting part of any sports competition. And so let's look at the statistics of lead changes. And here we can learn a lot of interesting things, and I will introduce you to some perhaps very surprising concepts in random walkology that you might not have thought of naively. So with lead changes, there's many basic questions you can ask from the point of view of a sports fan. How many lead changes occur? How long is one team in the lead? When does the last lead change occur? And if you're interested in real-time game betting, so this is maybe more relevant in Great Britain, where you can do this, you can ask, when is a lead safe? When should you call your bookie and say, I'm betting on this team because they have a lead of 10 points with 3 minutes to go, and I'm going to bet my house on that they're going to win. And we'll find out, is that really a smart thing to do? Okay, so let's look first of all at number of lead changes. So here is an idealized representation of the score difference. Again, here is time, here is the score, and the score difference is doing some kind of a random walk trace. Eventually, there's a final score in the game. So we're just interested in focusing on the lead changes and how many of them are. How many are there? Okay, so first of all, if we think about evenly matched teams, and for the rest of this discussion, I will only treat the case of evenly matched teams. And again, you can ask me critically, like, well, what happens if the teams are not evenly matched? I'll answer that later on. But if there's evenly matched teams, then the number of lead changes is equal to the square root of the number of steps in the random walk. Now, for basketball, a typical NBA basketball game has each team roughly about 100 points each. Each scoring event is typically 2 points, and it means there's roughly 100 scoring events over the course of a 48-minute game. So if n is 100, m would then be 10, roughly speaking. And here is sort of the justification of why it's a square root of n, because let's just look at the probability distribution of a one-dimensional random walk of n steps. And what we want is the probability being at the origin, that is when a lead change occurs, and we want to add up the probability being at the origin from any time n up to the total number of events in the game. So since this scales at the origin like 1 over square root of n, we're integrating square root of n, and so we're integrating 1 over root n, so we get root n as the answer. So again, for basketball scoring, with a roughly 100 points, 100 events in the game, there's roughly 10 lead changes. So that's the times that you really might want to watch the game when lead changes are occurring. But now comes a little bit of a subtlety in basketball, which is different than what happens in soccer, which you call football here, I guess, or in ice hockey. Has anybody ever seen an ice hockey game? Very few of you. I'm Canadian. Canada's national sport is hockey. We live and die for hockey. This is a game where, and the same as happens in soccer, when a score happens, the ball is returned to the center court and the two teams compete equally for the possession of the ball or the puck. So if team A scores and the probability that it scores next, the teams are evenly matched, it's just 1/2. But in basketball, there's this new feature, anti-persistence. Namely, when one team scores, the other team gets possession of the ball. And so they have an overwhelming probability of actually scoring next. Actually, it's not overwhelming, but it's still significant. So when team A scores, team B scores next with probability which is roughly 2/3. And the same team scores again in succession with the probability roughly 1/3. So that's an important number that characterizes basketball scoring. And so it turns out that if you use this anti-persistence and build a random walk model, the so-called anti-persistent random walk, write down the master equation, which hopefully you have a sense how you might go about doing it, and then solve for the diffusion coefficient, it turns out that the diffusion coefficient is modified by this factor 1 minus p over p, which is roughly a factor 2, because it's 2/3 over 1/3, so it's 2. When I take the square root of it, I'll get another factor, root 2, more lead changes. So according to this trivial model, there should be roughly 15 lead changes in a typical NBA basketball game. Now, yeah, question? Yes, so if we're talking about truly Brownian motion, they should happen infinitely close together. And let me come back to that point a little bit later on. But yes, the times between lead changes also have the same kind of scale invariant property that Brownian motion has. So one can go a lot further with this. One can look at the distribution number of lead changes. And so I'm not going to derive this, but let me just tell you that this is a very nice book by George Weiss on random walks, and he derives this result that the typical number of lead changes is root n, and the distribution of number of lead changes is a Gaussian function. By the way, is this going in and out as I'm talking, or is it's clear at the microphone? It's okay? So using this modified diffusion coefficient with anti-persistence, we just take the well-known result that was derived by Montrol and Weiss in the 60s, and with anti-persistence, we get this Gaussian distribution. And here now is a comparison of NBA game data in the red triangles with this idealized theory, and the blue circles are just doing simulations of many seasons of basketball building on an anti-persistent Poisson process, which is essentially mimicking the actual microscopic scoring events. So the sort of the faithful microscopic model fits the data very well, or mimics the data very well, and this very naive theory fits the data pretty well as well. So anyways, that's one amusing feature. Another feature, yeah, question. The black curve was this, Gaussian distribution. The black curve in what? The blue circle is a result of actually doing a simulation of an anti-persistent Poisson process. So we say that there's a certain rate of scoring, which is roughly 0.3. We build a Poisson process where we make the scoring events, but we build in the anti-persistence as well. So here's another one, which is really, when you first are exposed to this, you'll be very surprised, I hope, which is you can ask, how long does one team lead? So in this game, Denver raced to a huge lead, was leading almost, more than 3/4 of the game. Then there was a bunch of lead changes. And so the question I want to ask is that, what is the probability distribution for the time that Denver was in the lead? So in this game, Denver was leading all the way up to here, then Chicago took the lead, so then Denver was leading again, and finally Denver led at the very end. And so what I want to ask is, what is the length of this stick compared to the entire length of the game? What is the probability distribution of the length of this stick? Naively, you would say, well, if the teams are evenly matched, this stick should be, average value should be 1/2. And then what is the distribution about 1/2? It ought to be symmetric, right? Because there's no bias. And so we can ask the following question. What is the probability that a team is leading a fraction of the time? What is the fractional length of the stick? What is its probability distribution? So is it this? Right? So what do you, so is this, do you think this is the right form? Oh, you want to, but it has to be symmetrical though, because both teams are evenly matched. So I see lots of people doing this, and so maybe you know the answer, but let me tell you what the data says. So here's the data. So this is, again, the probability that one team is in the lead as a function of the game time. And yes, it's an upside down curve. It's nothing like a single peak. And, it's when I was first exposed to this, for my first 10 years in my career, I worked on random walks. And after 10 years, I thought, boy, I think I know something about random walks. Until I was exposed to this, I realized I knew nothing. And so it's useful to have these sort of hits over the head every once in a while that you realize you know a lot less than you think you know. But one nice thing about this is that this is now the theory that comes from something called the arcsine laws, which some of you have work in this area, and it's a very beautiful facet of random walks. And so if I have a random walk of time t, this is the exact probability that the random walker is on one side of the y-axis of the, or maybe the score difference is positive for a time t of the entire game. And a nice feature about this arcsine law is it's a zero parameter fit. There's nothing to fit here. I just take the actual, theoretical expression and fit it to, and the data, perfect match. Here's another one, which actually is simple enough that there's a trivial derivation of it, so I'd like to actually go through it because it's a nice application of the theory of first passage. And that is, when does the last lead change occur in a basketball game? So here we have a idealized basketball game. There's a bunch of lead changes. Then at this point of the game, a team takes over and it's leading for the rest of the game. What is the distribution of times for this last lead change? When might it occur? Naively, if I didn't, based on what I knew about basketball before I did this study, well, I said, well, the teams are trading a lead 15 times a game. And so if there's 15 lead changes, the last lead change should be somewhere around here, near the end of the game. And so the distribution of the lead change should have some peak near the end of the game, or the distribution of times for the last lead change. But let's now use physics to calculate and see what happens. So first of all, in order to have the last lead change that happened at time t, it must be that at time t we have a tie. So that means that the random walk has returned to the origin exactly at time t. And then we must have that the rest of the trajectory never touches the origin. And the way to represent this is, let's work backwards in time. We have some unknown final point, and we have a trajectory which comes to the origin for the very first time in time capital T minus little t. So when we reverse time, we have a first passage path that starts anywhere and ends exactly at the origin. And we just have to compute the probabilities of these things. And so let's do that. So this is 1 over square root of 4 pi t, because it's just the random walk propagator at the origin. And for this guy, well, it's this is the first passage probability. And maybe some of you know about this, but if you don't know about it, let me just sort of briefly derive it, which is first of all, this is the familiar occupation probability of a random walk. And I apologize that my notation might be a little bit jumpy, because sometimes I call this P, sometimes I call it C, but this is the probability that the random walk is at position X at time t, just a Gaussian. Now from this, we can derive the first passage probability easily, which is in the framework of a one-dimensional random walk can be cast as the following question, which is you start with a random walk at some arbitrary position, x0, and ask, when do you come to the origin for the very first time? What is the probability distribution of the time to come to the origin? So when does a random walk first hit the origin? And the way that you can calculate this with essentially no work is, here is my random walker that starts at position x0 and is coming to the origin at time t. So if there was no constraints on the system, the concentration or the probability would just be a Gaussian centered at x0 because we started x0. But we want to come to the origin for the very first time. We don't want it to come to the origin ever before then. In order to impose that, we must impose what's called an absorbing boundary condition at the origin. That is, the random walk never hits the origin until this final time. And the way that you can guarantee that is that you launch an anti-Gaussian at minus x0, which does the mirror image path. And so here is the anti-Gaussian centered at plus x0. And so this guarantees that the concentration at the origin is equal to 0. What we want to compute is the probability that the random walker actually hits the origin, which is the flux, the diffusive flux here. So the first passage probability is nothing more than the diffusive flux at the origin. And so we calculate the first derivative of this, and you get this quantity, x over t to the 3 halves, e to the minus x squared over 4 dt. That is called the first passage probability. That is the probability that a random walker first hits the origin at time t. There's two outstanding facts about this first passage probability. First one is that you are guaranteed that if you wait forever, the time integral of this first passage probability is 1. You always hit the origin. So that means you launch a random walk at some arbitrary point, you're always going to hit actually every point on the one-dimensional lattice, and in particular the origin. But even though you're guaranteed to hit the origin, the average time to hit the origin is infinite. This dichotomy between certain return but waiting forever for the return to happen is what makes the one-dimensional random walk so rich, and even if you think you understand it, you really don't until you've read Levy's book in French and realize that there's so much lurking behind some simple statement like this. Okay, so now we're back to here, and so all we have to do now is we want to take this and integrate over all starting positions, because that's the thing that's sort of the free thing here. So the probability that the last lead change occurs at time t is just this, we have to integrate over all final positions of the walker, this time reverse first passage, the probability being at the origin. This is just elementary calculation. Again, you get the arcsine law. And this is called the second arcsine law, even though it's mathematically the same as the first arcsine law. So let me now show you data. This is NBA data of the probability the last lead change occurs at time t. And you see that it's, again, a U-shaped curve. What's cute is that we did lots of different simulations. And so this is simulating a homogeneous Poisson process. And you see it fits the data pretty nicely. But we can actually include the glitches that seem to happen at the end of the first half, the end of the 3/4, the end of the first quarter, by actually simulating an inhomogeneous Poisson process. And we take the instantaneous scoring rate at every single point in the game. And so we can actually get microscopic fidelity with the data. And then here is the actual arcsine law itself. So everything fits very nicely. Let me now tell you, this is now a theoretical physics slide, why there should be 2 peaks for the distribution of times between, for the time of the last lead change. And the key to understanding why there should be 2 peaks is you just should plot the data in the right way. So I'm plotting now score difference, not as a function of time, but as a function of logarithm of time. And the reason I'm doing that is that the time between lead changes is growing like root t. And so they're getting further and further apart as a function of time. So if you plot it versus log t, then there's sort of a characteristic distance between lead changes in this logarithmic scale. And now here in this particular example, if here's where the game is finishing, then there was a lead change just before the end of the game. So for this particular trace, the last lead change happened very near to the end. But now here's another trace, and what I argue is that here the last lead change is here, but on a logarithmic scale, this is many orders of magnitude way down there, and so this means the last lead change occurs near the beginning. So no matter how you draw these random walk trajectories, you have to arrange things very carefully to have the last lead change halfway in the game. Typically in these plots, you'll either have the last lead change just before the line or some finite distance away from the end of the game, which would correspond to a lead change at the beginning of the game. So this is a simple way of understanding why there were two peaks. I'm going to go by this quickly. You can ask, well, what about different team strengths? All of what I did for you, you can do the same calculation for unequal team strengths. It's a little bit more involved, but you can do it. Then you can look at what this distribution looks like. It's still this U-shaped curve. Then what we can do is average over all the team strengths, and after you do that, you can't see any difference with equal team strengths. Last thing that I want to present is, when is a lead safe? So that is that we have a game going on. At this point in the game, the lead size is L. There's a time tau left in the game. Can I go to call up my bookie and say, I want to bet my house on that my team that's leading now is going to win at the end of the game? Should I do that? So that's the basic question I want to ask here. So this is quantified by this probability that a lead L is safe when a time tau remains in the game. And this is easy to calculate because the probability the lead is safe is 1 minus the probability that the lead is not safe. And this quantity is the probability, this is the first passage probability. So that means that starting at a distance L away, this is the probability that a random walk comes back to the origin for the first time at time t, and I integrate up to tau. And so this is the probability the lead is not safe. 1 minus this is the probability the lead is safe. And for the simple random walk, this is a sort of very elementary calculation, and you just get the error function. Error function of z, where z is like the scale of the lead size. So the natural measure of how big a lead is the size of the lead divided by the square root of the amount of time left in the game. And so here's what this looks like. This is the error function. So as the lead size increases, the probability that the lead is safe is approaching 1. And to give you a sense of numbers, if you have a 10-point lead, so this is 10-point lead with 8 minutes left in the game, your lead is safe with a probability 90%. So that's when you can go call your bookie and give them 9 to 1 odds, and you should be okay. Here is the NBA basketball data versus this really trivial 3-line theory, and you see that it matches extremely well. When I give this talk in the United States, everybody knows who this guy is. He is a guy who popularized doing quantitative analysis of sports, especially in baseball. So he got famous for developing the metric that's shown here of when a lead is safe. And so this is Bill James's metric, which people actually bet money on this. And here's the data, and here's our theory. So anyways, can basketball be described as this random walk? And I would say yes. But I'm not done. I have 10 minutes left, right? There's some buts. And so now let's come to some buts, because, when I give this talk in the United States, there are people in the audience who know much more about basketball. And by this time of the talk, they're like boiling mad at me. What about this? What about that? At least here, I guess there's not too many basketball experts, but let me tell you some interesting buts. First of all, there was the anti-persistence. So the point about anti-persistence is it induces a short-range correlation in a random walk, but if I'm looking at long-time properties, short-range correlations don't matter, so we still expect pure random walk behavior, modulo like a modification in the diffusion coefficient. So that's one feature. But now comes another feature, which is actually very prominent, which is that if you look at basketball, and for those of you who actually have watched basketball, especially NBA playoff basketball with teams that are fairly evenly matched, the first 45 minutes of the game will take an hour and a half. The last 3 minutes of the game will take another hour long because they call timeouts and this and that and fouling and whatever. It's like incredibly tedious. And the last 2.5 minutes of the game are very anomalous because if the losing team has any chance to win, they employ desperation tactics. And so to give you a sense, again, look at the scoring rate, and you see that at the end of the game, the scoring rate goes way, way up, even though the game is really slowed down in real time because, they call timeouts and they foul players and, the game seems to take forever. But there's a lot of scoring and in a little game time. So the scoring rate is roughly double in the last 2 minutes of the game and then the rest of the game. And so here again was this linear growth of the score difference, which has this anomaly in the last 2.5 minutes of the game. And here's an even more dramatic demonstration of that, which is let's now look at the probability distribution of the score difference at different points in the game. So because we think that the score difference is undergoing a random walk, the probability distribution of the score difference should be a Gaussian distribution. And so here, delta is the score difference, and I'm plotting it in scaled units divided by square root of 2dt, where d is the diffusion coefficient of basketball and t is the game time. And so at the end of the first quarter of the game, it looks pretty Gaussian. At the end of the first half, also pretty Gaussian. At the end of the third quarter, pretty Gaussian. At the end of 45 minutes, pretty Gaussian. But the last 2.5 minutes, something crazy happens, and this is what happens. So the last 2.5 minutes of basketball have almost nothing to do with the first 45 minutes of basketball. Another thing is that teams are typically unevenly matched. But the point is that, once you get to NBA, the very worst team can beat the best team on a bad day. That's one point. And if you look at the worst team in the NBA, and like if you go to a sports bar in the United States, you'll have these big fat guys with big beer bellies, and they're drinking beer, and they say, "Oh, that guy's an idiot. He doesn't know what he's doing." The guy who's an idiot who doesn't know what he's doing is this unbelievably trained athlete. Can do things that we could only dream of possibly doing. So the point is that there's a lot of filtration to get from pee-wee basketball to the NBA. You had to first excel in high school, you had to get a college scholarship, you had to be a college all-star, you had to be drafted. So the point is that the variation in the quality of the players is really quite small. So teams are typically unevenly matched, but the point is not that unevenly matched. And as it turns out, their differences even don't matter. So let me mention one other feature of basketball, which probably it sounds very natural, that if a team has a huge lead, then they tend to coast because we have a huge lead, let's just slow down the game. Whereas a team that's behind is desperate. And so if you look as a function of the lead size, what is the scoring probability? So if a team is winning by 40 points, which is like an unbelievable blowout, its scoring rate is much lower than if it's losing by 40 points, in which case the losing team is getting pretty desperate. So there is a systematic trend of the scoring rate as a function of the lead size. And we can use these last two effects to actually make a microscopic model to play basketball millions of seasons and try and compare this toy model with real data. And so I'm going to very briefly, in like the last 5 minutes, just outline a computational model in which our basic variable is we have an ensemble of teams of a given strength, x sub alpha. And what we want to compute for a team, when two teams play, what is the probability that team alpha wins the game? So there is a traditional model of real competition, sports competition, life competition, that you have two teams of strengths XA and XB. The probability that A wins is just the strength of A divided by the sum of the strengths, and probability B wins is the strength of B divided by the sum of the strengths. So this is called the Bradley-Terry model of competition. And what we've done is we've just modified to include natural features that we see in basketball. First of all, there's the anti-persistence. Namely, if I just score, then the probability I score next is reduced by this anti-persistence probability. And then there's the additional feature of this like return to zero. And if you take this, and now you have like 30 teams in the NBA, you make some assumption, and let me make the minimalist assumption. First of all, the absolute value of the team strength doesn't matter, so let's choose the average strength one. And let's assume a Gaussian distribution of team strengths, and let's try and fit the width of that distribution such that we can match NBA basketball scoring data. And so here's our only variable, the variance in this team strengths. And what I'm showing you now is a result of like simulating millions of seasons of NBA basketball and comparing observables with things that we see in basketball scoring. So for example, there's lots of different observables, but we look, for example, the time that one team is in the lead. And what I'm plotting here is the deviation of the time in the lead in our toy model with what we see in NBA basketball when we vary the width of the team strength distribution. And all these different variables seem to have a minimum at roughly the same point. And so it seems to suggest that to describe NBA basketball scoring statistics, we just take an ensemble of 30 teams, we give them average strength one, a Gaussian distribution with a variance here 0.0 whatever it is, I can't, 0.008. And we take that and we can then essentially reproduce everything in NBA basketball scoring. So one other point about this is that 2/3 of all team strengths are within 9% of 1. This gives you a sense of the smallness of the variation of team strengths. The very best team in the NBA, the Golden State Warriors, who won the NBA championship, and they won a lot of games in their season, but they're only like 20% better than the worst team in the NBA, according to all these measures of observables in basketball. So perfect timing. Can basketball scoring be described as a random walk? So my answer is still yes. Thanks for your attention.
Yeah, questions? Yeah, so you spoke about the hot hand, right?
Yes.
So there's a paper that came out pretty recently. I read an article in ESPN about it. Paper is by Miller and Sanjib, where they analyze the three-point contest, and they say that the principle of risk, the NBA three-point shooting contest that happens,
Okay.
and they concluded that there is an hot hand, and it occurs fairly occasionally as well.
Yeah.
Using, they said that the way the data was analyzed before was not correct because there is something known as the restricted, the principle of restricted probability. So when they included that, they concluded that there is an hot hand.
Yeah. So I guess what I would say, so the question was, is that in the NBA three-point shooting contest, which happens in the All-Star game, they have players line up from very far away and they try and sink as many baskets from a large distance, and they say they found a hot hand. And so in fact, the original work of Gilovich et al. Was 1985, and it was based on just looking at observations and writing stuff down by hand. Since that time, many studies have tried to either refute or verify this, and it is true that in the past couple of years, studies based on much more data, and sometimes studies based on much less data, seem to suggest that there's some deviation from the hot hand. But if there is a deviation from the hot hand, it is sort of, it's within the resolution of what I can see in this kind of a study. So I think the issue about hot hand is still open, but it's, these basic quantities, random walk quantities that I observe, it's insensitive to the very minuscule degree of hot hand that might exist if it really does exist.
The same things would...
Well, okay, so in fact, we analyzed 4 major sports leagues. We looked at NHL hockey, because I'm Canadian. We looked at college football. We looked at NFL football and NBA basketball scoring. NBA basketball scoring is the best data set because there's the most scoring events. And so that's why we looked at it. Hockey kind of begins to show the same kind of features as NBA basketball. But, in a typical hockey game, the score is like 2-1 or 3-2. So if we had 1 million years of data, we might be able to do the same kind of talk, but I'd have to wait 1 million years to give that talk. I mean, are you talking about soccer? Yeah. So water polo. Water polo. Well, certainly, I mean, there's lots of sports out there. I mean, part of the reason that we looked at NBA and NFL is that it's all categorized and it's all put on a easily downloadable form on the web, on their websites. So if there is water polo data that I could download, then I might take a look at it. But it's just that I invite you to take a look at it. You don't want to do it.
Hi. So I'm not really clear why there was a high probability for last lead change to occur in the beginning of the game.
Well, again, I would just refer you to that kind of scale invariant picture. You have an oscillating signal, and when it hits the origin, an amazing feature about random walks is when you hit the origin, I mean, if I'm talking about continuous Brownian motion, then you hit the origin infinitely often in 0 time, and then you move away from the origin, and the size of these intervals where you are away from the origin are growing like square root of t. So when you look on a scale invariant, logarithmic scale, then these sojourns between returns to the origin are roughly equal length. And then you have to just say, when I just put an arbitrary end to the game and as I take now an ensemble of trajectories, where is the last lead change? And you have to, you know, the typical thing is either the last lead change is right now, or if it's like some finite distance in the past on a logarithmic scale, it means that it's very much at the beginning of the game. So you just have to think in logarithmic time to appreciate why there is this peak at the beginning of the game.
Is there a huge asymmetry? I guess like 1 or 2 players scores all the goals. Is it? I mean,
yeah. Okay.
scores,
So
is it true?
I mean, you know, now we're getting into kind of real sports, which I'm not much of an expert in. But you are correct that basketball has some idiosyncratic features that other games don't have because one player can dominate. And so, you know, there was a well-known example of Wilt Chamberlain in 1962 scoring 100 points in a single game. And the whole team scored another additional 40 points or something like that. So you can be dominated by one player, and then there's maybe less systematic effects in one player. But again, when you integrate over the team and integrate over these 9 seasons of NBA basketball scoring statistics, these idiosyncrasies of one exceptional player get washed out.
The question, so I mean, can one actually use this analysis to for like making betting strategies and make money?
It's right there. You know, that was which slide was that? Back here somewhere. This thing about the last. No, I'm coming to it. I'm getting there. There it is. So yeah, I leave this as an exercise to the interested person to like make money out of this. So you have to move to England where they have real-time betting, and you have to go to a bookie that is actually betting on NBA basketball games, and you would clean out Bill James here. So I leave it as an exercise for those who are interested in money.
It was fun, and so let's thank both Sid and